Okay.
Uh, um, Good afternoon to everyone. I'm sorry for a few minutes late. I welcome all of you to the 37th lecture in the lecture series in nonlinear dynamics conducted by Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Dr. Badam Singh Kushwaha from IIT Dhanbad, which is formerly known as Indian School of Mines. Dr. Badam Singh Kushwaha is an applied mathematician. He obtained his PhD degree in mathematics from Bihar University, Muzaffarpur, in the year 2007. After working in Gwalior and Raipur for a couple of years, he joined as a senior lecturer at IIT Dhanbad. Right now, he is serving as a professor. Dr. Kushwaha is working on several topics in dynamical systems. To name a few, I spell out, he works on problems arising in celestial mechanics, dynamical astronomy, orbital mechanics, and high performance computing. Right now, he is also started working on machine learning. He has guided several students and for PhD, and right now supervising 6 students. From his CV, I understood that Dr. Kushwaha is largely investigating astrophysics problems from nonlinear aspects. I think today we are all going to hear the applications of nonlinear dynamics in astrophysics. When I inquired Dr. Kushwaha about the possibility to deliver a lecture in this forum, he immediately accepted. For that, I express my sincere thanks to him. With this short introduction, now I invite Dr. Badam to deliver his lecture. Over to you, sir.
Thank you, sir. Okay, so today's topic will be on space trajectory transfer using dynamical system theory. Here, our main objective will be to design trajectory as well its transfer using dynamical system theory. That means mostly traditional trajectory are transferred using, say, source to destinations by some specific thrusters or giving impulses, say single impulse, double impulse. That means they require fuel for transfer of the trajectory. But if we are using dynamical system, that means we can use our stable or unstable manifold for designing trajectory as well as transfer the trajectory from one place to another place using very less fuel. Because in that case, if some trajectory is going from one place to another place, that means it may be transferred through some, say, unstable manifold, and at the destination it will be captured by the stable manifold of that particular, say, orbit. Okay, so that will be our main objective of this particular talk. Now, basically, as I have seen in that particular invitation, that first we have to discuss about the basics of different things which we are using in our space dynamics. Then we will use its applications so that the student can understand what is the main advantages of the dynamical systems in, say, some specific field of celestial mechanics as well as orbital dynamics. Now here I think most of the students are from, say, numerical this dynamical system related fields, and they know much about the dynamical systems, and they may also have some knowledge of the phase space equilibrium points, then their stabilities. And main concern is here the fourth topic, that is trajectories, and mainly we will find different kind of orbits. We will have periodic orbits, quasi-periodic orbits, and some other planar orbits, and those orbits will be used to stay or to place our say specific object, say satellite, so that it can be there for a long time with small effort, and that effort will be simple perturbation. That small perturbation will be used to to maneuver that particular object around that particular orbit. Okay, because this is the main advantage of this our dynamical systems, that if this particular system is, say, very sensitive dependency of the initial conditions, that means small perturbation can also give much effect on the dynamics of the system. Okay, so that is the main things. Next we will have here invariant manifolds. That means here our trajectory transfer will be done using invariant manifolds. So we will discuss little bit about the invariant manifolds, and here those manifolds will be obtained using different high order numerical methods, so that there should be less error while computing the particular orbit as well as invariant manifolds. So these particular things may also be, you can say, seen in NASA's Genesis missions, where they have used this invariant manifold to transfer the Genesis trajectory from L1 hollow orbits. Okay. Similarly, here IS EE3 in 1978, that hollow orbit is used for inserting this IS3 International Space Explorer 3 spacecraft around that particular hollow orbit. Now here, what we will do here. Okay, so just we will see. Say we will have here x dot equal to say fx or say t. In our celestial mechanics, generally we will use non-autonomous systems. So that means here we will have x dot equal to fx only, where x will be from some space. So say n dimension space. But in general, in our space dynamics, we use 3 dimensions. That means it will be R3. Or sometimes our orbit will be planar, so we may use only xy plane. So that our dynamics can be seen inside that particular plane only. Okay. So this is our say dynamic systems, and I'm not you can say defining the dynamical system in detail. Only I want to see different specific kind of things which will be used in space mechanics. Okay, so if x is equal to fx and x is in Rn, then we will also have say some initial condition, that is xt0. So this particular whole thing, that means this x dot equal to fx and xt0 equal to x at x0. So starting from this x0, we will find a specific kind of flow. That means so at t we will have this value, and this will be obtained by solving our differential equations with initial conditions. Now we will have equilibrium point. So it will be simply fx equal to 0, where x dot is our 0. That means all the things are in rest. So it may be considered as x bar. So we will have, say this is x bar. It is equilibrium point where our right hand side function is 0, and we will have different kind of, you can say, things of x bar, that is equilibrium point. That means we will see stability. So stability may be your Lyapunov stability, or we will have here asymptotic stability for say autonomous systems. But for non-autonomous systems, this equilibrium point may not be there. It means this equilibrium point is related to autonomous system only, and this equilibrium point will be our, this equilibrium point will be equilibria in non-autonomous system. So it means it is nothing but there will be some freezing time points. Say x dot equal to f x t, where x in Rn and t from R. In that case, this t is extra dimension here, and that means this x dot equal to fx t explicitly depends on time t also. So this is non-autonomous systems. For that particular systems, we will have f x t equal to 0 at some particular time. Say it is t bar at say x bar and t bar. That means here x bar t bar is a specific point. So we can say it is freezing time. Okay. But hello. Okay, anyone want to say something? Anyone, any participant want to say something?
No, I think you can go ahead.
Okay. Okay, so that means for non-autonomous systems, this equilibrium point is not, you can say, exist. It is only for autonomous systems. If you want to say some equilibrium point is exist in non-autonomous system, then it will not be equilibrium point. It will be actually equilibria, where some specific time is considered at which that particular equations may hold. That means, say we will have say x dot equal to t minus x. So this is our differential equations. So if you want to find equilibria for that particular system, in that case, t minus x equal to 0. That means x equal to t will be a solution, but it will not a solution. It will be freezing time. X equal to t. So t is here, x is here. Okay, but here it, if you want to find actual solution, that solution will depend on you can say different conditions. That is not actual solution. Solution will be different. So this is not your equilibrium point, but it is simple equilibria. For some particular time t, you will get this x dot equal to 0, but for other times you will not get. Now we will see some specific points related to stability. So can you anyone tell me about the stability of equilibrium point?
Yeah.
Tell me.
Madam,
Okay.
yeah.
Anyone?
No questions so far.
Okay. No one wants to say. So whether these specific things we should define, or we can go ahead.
Yeah, you can go ahead.
Okay.
Yeah,
So,
sometimes the student asks at the end of the talk.
okay. That means there is no need to ask, na? Because if they have some query, they might raise the query. Okay, no problem. Okay, so we will see equilibriums or equilibrium points. So suppose we will have x dot equal to fx, and we will have, say, this is our x, and say by will be another solutions nearby this by. That means here nearby x. So if we will have x t0, that is initial point, means at the time t0, and by t0 at the time t0, and we will have this modulus less than delta, then we will have xt minus by t should be less than epsilon for all time t is greater than 0 or t0. That means, so we can say Lyapunov stability if for given epsilon positive, there is delta positive, such that this delta may depend on epsilon. So if this particular trajectory is starting from say x0, okay, so suppose this is the trajectory which is starting from x t0, and we will have another trajectory which is starting nearby, say this is y0. So it's starting from here and it remains here. That means in a particular neighborhood. So that will be your Lyapunov stability. Now we will have next asymptotic stability. We will have same cases. That means for given epsilon positive, there exists delta positive, such that x t0 minus by t0 less than delta implies that limit of t tending to infinite, this xt minus by t mod should be 0. It means here if we have again some point x t0 here and another point say y t0 here, and if we are having some say specific cube kind of things, and if this trajectory is approaching to xt0 or xt after some time, in that case it will be asymptotically stable. That means we can write here xt is here and this is yt. So it is approaching to xt. So that will be asymptotical stable. But
So
here,
is this the same as linear stability?
no, it is not same, because sometimes it may be possible that some orbit, say some orbit may start from nearby. Just a minute. Suppose this is orbit starting from, sorry, this blue one is orbit starting from say x t0, and another one is say red one. It is starting from say by t0, but it may never, you can say, meet for a long time. So that will be your simple linear stability or simple stability. But if we are calling that if this trajectory converges to the trajectory starting from xt0, then it will be asymptotical.
No, in linear stability also, asymptotically for large time we require the perturbation to die down, which means it approaches the. Yeah.
But it is not mandatory to converge to that particular point. It may be around that, but it may, suppose we have say two this limit cycles, say, okay, or you can say two periodic orbits. So this is nearby trajectory, but that may never meet the other trajectory. It may start nearby and it will go around that. So it is stable, but not asymptotically stable. Are you getting this?
Yeah. Oh.
Because we have started, it may start nearby, it may start, but it is not reaching the point, equilibrium point. It is never reaching here.
Yeah, but linear stability requires that the perturbation die down. That means it comes back to the original state.
It is gone down. Means it may be decreasing, but it may not equal to. It may not reach at the equilibrium point. But in asymptotic stability, always at the end, these two things will be very near.
Okay.
Okay. So we will see if say okay. So as you are talking about the linear stability, that means here if we have say x dot equal to fx by and y dot equal to gx by, where x by from R2, say we are considering only two-dimensional space. Okay. And if we have linearized f and g using our Taylor's expansons, then say linearized part is ax plus by and y dot is cx plus dy. And we have some second order terms, second or higher order terms, x by in power 2 and plus here again x by in power 2. Okay. So here we will consider only this particular portion to check the stability. So that stability will be obtained by considering the matrix x dot equal to say a f at x0. Oh, sorry. D of fx. Okay. D of f at x0 into x. So this d fx0. So this is d fx0 is nothing but it is our matrix A, B, C, D. Okay, so that is actually Jacobian matrix. Jacobian matrix. Okay, so to find the stability of equilibrium point, so we require the eigenvalues of eigenvectors should be obtained from this Jacobian matrix, and we will have some solutions. Say xt will be c1 e raised to lambda 1t plus c2 e raised to lambda 2t, and yt will be similarly c3 e raised to lambda 1t plus c4 e raised to lambda 5t 4t. Oh, okay, 2t. Sorry. Okay, this is C4. That means here this particular things maybe, or it depends on the kind of lambda 1 and lambda 2 we are using. And suppose case 1, we will have say lambda 1 and lambda 2 both are positive. Okay, in that case what will happen? If lambda 1 and lambda 2 both are greater than 0, in that case we will have unstable orbit. Na? That means here if we will have x dot equal to say x and y dot equal to say y, that means we will have Jacobian j equal to 1 0 0 1. So in that case lambda 1 will be 1 and lambda 2 will be also 1. So what will be the nature of this equilibrium point? Can you tell me? What will be the nature of equilibrium point? If both are positive, lambda 1 lambda 2 both are positive, then what will happen? Anyone?
Be unstable.
Unstable means which kind of unstable? Means unstable. Can you tell me the kind of, because we have not shown here phase portrait, hai na? Actually, if we want to design the trajectory in phase space, say our phase space is say R2. If we want to design this trajectory in R2, this is say R2. Okay. In that case, it will show the nature of you can say trajectory we are finding, or we are you can say discussing. Say equilibrium point is here. Equilibrium point is x equal to 0 and y equal to 0. That means this is 0 0 equilibrium point. Okay. So our solution will have like this, that xt will be e raised to lambda 1t, and second solution will also be lambda 2. Okay. So if we want to write say lambda 1t, so then what will happen? It will increase very fast, because here x dot is x, so it will be like this. Similarly, if I am taking some point here, so again it will move there because the velocity will have positive side. Similarly, if I will take y equal to say negative value here, so it will go like this. Similarly, I am taking some x positive here, in that case it will go like this, and it is go like this. Suppose I am taking x and y both positive, so it will go like this. Okay. Similarly negative, so it will go like this. Okay. It means it is what? It is unstable node. Unstable node. Okay. What happens if our values of these lambdas are say increasing? Can you tell me? We say 1 is 1, lambda 2 is say 2, lambda 1 is 1. Then what will happen? Say I have this is dynamical system, x dot equal to x and y dot equal to 2 times of y. That means in that case lambda 1 is say 1, lambda 2 is 2. Okay. Then what will happen? In that case, one solution, simply direct you can say xt will be e raised to 1t and yt will be e raised to 2t. Okay. So you can take square of first one and divide it. So that means we will have x, say c1 c2 is here, c1 c2. Okay. Or you can write simply e raised to t x0 and here y0. So whenever you multiply, you square this and divide by this, then you will see x square by y equal to say x0 square by 0, or you can say this is some constant, say that means y equal to some x square x0 square by y0 and x square. Okay, it means it is one kind of parabola kind of things. It will be not, but the branches will be like this. In negative side, you will see like this. Okay, so it depends on the kind of eigenvalues we have. If one eigenvalue is suppose larger, that means magnitude is say larger, then in particular directions it will be stretched, and in other directions, suppose this lambda 1 will be suppose 0.1, so that means it is in other direction it will be decreased. Okay, so what is the case when lambda 1 is greater than 0 and lambda 2 is less than 0? Then what will happen? See, that is the case. That means x dot equal to minus x and y dot equal to say y. Then what will happen? Equivalent point is 0, 0. Anyone tell me? Monisha? No. Okay, so that means here we will have x bar is 0, 0, and we will have Jacobian j, that is minus 1, 0, 0, 1. Okay, so that means lambda equal to plus 1 and lambda equal to minus 1. So we will have these two equivalent points. Two, not two equivalent, two, sorry, one equivalent point, but two eigenvalues. One is negative, another one is positive. So what will happen in that case? You will see solution that will be x0 into e raised to minus t, and yt will be y0 e raised to plus t. Okay, so here we can draw the first phase portrait when x is negative. In that case, what will happen? If x is negative here, so it will give the value positive. That means x dot is positive. X is say negative. In that case, x dot is positive. So we will have this arrow this side. Okay. Similarly, x is say positive, then x dot is negative. It means if I am taking some point here, nearby point, so it will go like this. Similarly, I am taking say y. Y is say positive. In that case, y dot is positive. So suppose we take some point here, so it will go like this. Similarly, it will go like this. Okay, if I am taking some point here, so what will happen? It may go like this. Similarly, like this. So here we will have saddle point. Now this saddle point will be used to find stable and unstable manifold, because here this particular direction, one direction, this is stable direction, and this one is unstable direction. Okay, similarly we can also use different cases. That means whenever one value is larger than others, so in that case, in the particular direction it will be stretched, and other direction it will be compressed. So that is case second. So for finding the trajectories which follow linear, this stable or unstable manifold, first we have to find the equivalent point of the system. After that, we find the eigenvalues or eigenvectors of that particular Jacobian matrix. Then we will find the stable and unstable manifold. We will see later on how to find the stable and unstable manifold. So main concern was here to see which kind of points we will have. Here, case third will be case second, and that was case 1. Okay. So we will have saddle point if we will have one positive and another negative real values of this lambda. Now next is case second. That means whenever we will have complex roots, then what will happen? Complex Eigen values. Anyone? Tell me. If we have complex root, then periodic orbit. So can you tell me something about the periodic orbit? So we will have say A plus minus IB, or simply some other points, other things you can take, na? P plus minus IQ. Okay. So here our solution will be like xt will be, I will take one example so that you can understand. Okay, so we will have e raised to say pt and cos qt plus minus I sin t. If I am taking simple capital X, na? So there will be plus or minus sign, no problem, na? I sin qt. Okay, so what will happen? It depends on the value of p. This value of p plus I plus minus iq. It depends on the p, that is real part of lambda is equal to 0. Real part of lambda is greater than 0, and real part of lambda is less than 0. So can you tell me about these three things? For these last two things, two cases, is real part is not equal to 0, and for this case real part is 0. Then what will happen? What is the nature of equilibrium point if we say real part of lambda is not 0? Anyone?
Unstable focus, stable focus.
Okay. And there is some specific name for equilibrium point for this case? Hyperbolic, है ना? Equilibrium point, and it is non-hyperbolic equilibrium point. Suppose we have non-hyperbolic equilibrium point, then whether we are applying this you can say linearization analysis will applicable for nonlinear system or not? If suppose we have first case, that is nonlinear hyperbolic case, then whether this linearization will be valid for nonlinear case or not? Can you tell me anyone about this? Because you are considering your system of equations, that means this system. This is non-linear systems, non-linear system, and you have taken only the approximated way, that is linearized system. Okay, that means you are finding the nature of the normalized non-linear system by considering only linear system. That means if we have equilibrium point, say x bar here, so around equilibrium point you are finding the dynamics of the system. But if it is non-linear system, then this linearized system may be valid or may not be valid for long time or for a long time. So in which case it will be valid, and in which case it will not be valid? Can you tell me? Suppose I am considering the second case. Second means this is a second case and this is first case. Okay, so first I am considering second case. That means real part is greater than 0. Then what will happen? We will have solution with e raised to some positive things. Okay, some positive things, p is positive. Okay, t, and we will have cos qt plus I sine Q2 with plus minus maybe. Okay, so it means if we have equilibrium point, say here, so I am starting from say anywhere, and it will go like this, na? That means due to cos and sine, it will be, you can say, periodic, or it will generate a certain kind of things for all time. But due to this increasing radius, it will be always go far from the equilibrium point. This is our x bar. Okay. Similarly, this is case A and case B. In case B, real part is less than 0. So in that case, what will happen? You will have same thing, but the direction will be different. So I am starting from here, so it will go like this. Okay. So we will have focus, but this is unstable focus, and this is stable focus. Okay. Now next thing is first one. That is when, so for this case, for hyperbolic case, for hyperbolic equilibrium point, the analysis of linearized system will be applicable to the non-linear system. Another case, we will have first one here, case 3, first one. That means real part of equilibrium point, this eigenvalue 0. In that case, we will have solutions like this: cos qt plus minus I sine qt. Okay. Here sign of here immediate part is not very important. That means we will have lambda plus minus I q. So sign of this q is not very important here because it may not give a specific effect. So what will happen if we start from anywhere? Say I am starting from here, it will be always at that particular distance. Okay, say one distance. Okay. Similarly, we may have, I am starting from here, and it will go like this. Okay. So it depends on the value. I may start from anywhere, and here we will have x0. X0 will be there. Actually, I have missed here. You have to write. With this, you have to write say x0 because it depends on the x0. That is equilibrium point, no? So we will have, if we start from here, it will be always in a particular in this orbit. If we are starting from here, then again it will be in another orbit like this. That never you can say converges to in a particular point. So that will be actually periodic, or you can say limit cycle, na? But for nonlinear case, for conservative case, limit cycle may not occur, hai na? So you can say it is periodic. It is better to say it is periodic, na? Or center, because limit cycle may have different you can say characteristics. So you can say it is center, then, and it will be applicable for full region R. That means it is applicable for full region R. That means anywhere you start, and you always be on that particular, you can say, orbit. Now this is J. We will have A, B, C, D, and we will define T will be say lambda 1 plus lambda 2, and this capital delta will be say lambda 1 into lambda 2. So actually these two things are very important because they are invariant with any change we are making inside the dynamical system. That means if we can use any transfer or change of the variables, or we can use any manipulations, then this trace of Jacobi matrix, trace of matrix, and here determinant, both will be always invariant under the any transformations. Okay, so that means we can see if lambda square minus lambda 1 plus lambda 2, lambda plus lambda 1 into lambda 2. These are the things. So we can write lambda square minus t lambda plus this delta. Okay, so this will be our characteristic equations if we use determinant of j minus I lambda equal to 0. So we will have this kind of things. So this capital delta and capital T will be invariant under any change or any transformations. Similarly, their squares means squares say 1 order or 2 order or 3 order. All higher order is square of the trace will be, you can say, invariant under the any transformations. Here we have A B C D. So that means here lambda square minus A plus B will be there. Lambda plus AD minus BC will be there. So actually this is our determinant and this is our trace. Now we will design, or we will draw a graph. Because whenever we find this lambda will be plus t plus minus root of t square minus 4 delta by 2. So what we can write here, this is a parabola when t square equal to 4 delta. This is delta axis and this is t axis. Then that will be your t square equal to 4 delta. Now if we have said this lambda 1 and lambda 2 both positive, then what will happen? In that case it will be unstable case, that is right hand side. But for this case where lambda 1 and lambda 2, lambda 1 into lambda 2, that is delta, is negative. So for this case we will have saddle. Okay, for this that means the region which is below the this parabola in first quadrant, we will have unstable node. Unstable node. That means we will have this kind of thing. Okay. Similarly, we will have here unstable focus if it is complex conjugate and real part is not 0. Similarly, this is unstable focus. Here asymptotical stable focus will be here for this case. Okay, that means real part is negative, that is real part is positive, real part is positive, and real part is negative. Now here we will have what will be there? Anyone tell me? Here at the second quadrant below the parabola, anyone tell me? Where delta is positive and t is Oh, delta is negative. Oh, this capital delta is negative, and t is positive. Here t is negative. Sorry, t lambda 1 plus lambda 2 is negative. Sorry, but for this case, delta is positive here, and t is positive. Can you tell me, anyone, for this case, what will be the nature of equilibrium point? Anyone? Can you tell me? In this particular region, which is in second quadrant, where capital delta is less than 0 and t is greater than 0, what will be the kind of equilibrium point we will have? It is actually a stable node. We have not seen there. We can also define a stable node here. Case 1a, you can say this is A. In B, you can define case 1b. If lambda 1 is 0 negative and lambda 2 is also negative, in that case you will see this kind of graph. You will see phase portrait. It means equation will be x dot equal to plus x minus x and y dot equal to minus y. For this kind of things, you will see it is a stable node. Okay, so we will have here a stable node. And what about this line T? For this case, where delta is 0, can you tell me, anyone? For this line, this vertical line where delta is 0, anyone? No response, na? And delta equal to 0, it will be center. Okay, so but not below this line. Below means above this particular, that means t is greater than 0 and delta equal to 0. So for this case you can say it is center. But for this below this particular horizontal line, we will have saddle. This is saddle area. Okay, but the center is actually very much sensitive with the perturbation. If we use small perturbations, then it may go left hand side or it may go right hand side. That means here it may becomes asymptotically stable spiral or asymptotically stable spiral. So a stable or unstable spiral can be seen if we have center. Suppose this is center. Just a minute. Okay, so this is center. Now what happens? Sometimes if I am starting from here, so it may go like this. It may converge to equilibrium point, or it may go like this, and it may, sorry, instant. It may go like this, like this. Okay, so it may start from here. So now this is asymptotical, so it is unstable center, unstable, you can say unstable focus, and this is stable focus. This one is stable focus. That means here, if we take small perturbations from this periodic orbit, then trajectory may becomes unstable or stable. That means there will be qualitative change in the dynamics occur if we make a small change in say parameters. Okay, so that means these centers are very much sensitive. That means they are structurally unstable. So this linear analysis cannot be, you can say, that will not give correct result, or sometimes it may give confusing result if we are applying this linearized you can say theory for looking the nature of the center. That means whenever we will have real part equal to 0. Okay, this in non-hyperbolic cases. Okay, so in this case, what will happen? This linearized theory may give ambiguous results. That means it may be confusing, may not give correct result or analysis correct result. Okay, so if our equilibrium points is non-hyperbolic, in that case we should be very careful. That means here our period will, or our trajectory will be in that case center. It is also one kind of, you can say, periodic orbit. So if it is periodic orbit, then always be careful that we should apply some higher order method or some other methods for checking the stability and other things. You know? So for that purpose, we use Lyapunov function, you know, to check the stability of non-hyperbolic case. We apply Lyapunov function theory. Okay, it means it simply linear system theory will fail. That means it may be, sometimes it may give the correct result, but if you use small perturbations, then there will be qualitative change in the dynamics. Okay, so in our trajectory transfers, what we find? We find the equilibrium points and their periodic orbits around those equilibrium points. So generally we you can say we will be very careful while analyzing those kind of systems. Okay, next we will have here stable and unstable manifold. Right? So we have seen all the kinds of you can say cases. Here we have applied for 2 dimension. The similar theory can be applied for higher dimensions also. Accordingly, we can take two dimensions to understand this kind of phenomena. Say we will have 3 dimensions. That means we can take pairwise two dimensions, say in x direction, y z direction, or z directions. Or sometimes we can also use in 3 dimensions. Say in z directions, one eigenvalue is positive. For say in 3D, say in z direction, it is positive in z direction, and but in other cases, say lambda is p plus minus iq in x and y directions. In that case, we will have in one direction it is unstable, but in other you can say directions like in xy plane, it is one kind of, you can say, focus. Okay, so in that case, what will happen if you draw a face portrait? Then it may start, say that is x and this is y and this is say z. So you may start from anywhere. Say you are starting from here, and due to this lambda complex eigenvalues, so you may have this kind of focus stable or unstable, but this lambda in third dimension is positive. So that's why it will have z equal to say e raised to lambda t, say lambda t and z0. So this lambda is positive. So it means it will always you can say go to, or it will be expanded exponentially. Similarly, if we use xy directions, so that will be either unstable focus or stable focus. Suppose it is unstable focus, that means it will go like this, but due to this z is increasing. Okay, so this is sorry, this is for stable focus, na? Stable focus in x by direction, but in z direction it is you can say increasing. That's why you will see this kind of nature of trajectory. So this kind of analysis you can do for higher dimensions also. Okay, now we will have two more things here. We will have one is gradient system. Okay, can you tell me about the gradient systems? Which dynamical systems you call the gradient system? Anyone? Suppose x dot equal to fx. This is dynamical system. Then how do you can say check whether it is gradient system or not? If we have some function phi x equal to c, this is some scalar function. If I am writing this x dot equal to gradient of this phi x, if the system can be written, that means if fx can be written in form of gradient of some scalar function, then we say this system is gradient system. And what is the property of gradient systems? Can anyone tell me the properties of gradient system? Suppose we will have, this is the plan. This plan we will have, this is say delta phi x equal to c. For different values of c, we will have parallel planes or different planes. Okay. So what will happen if some point is here? Then gradient will show in this direction, normal to the surface. So that means this is delta phi x. Okay. So to see the solution trajectory for gradient systems, it will always be initiated with that particular surface, and it will be normal to that surface. So that means at x0 it is here, at xt you may have some other surface, say this is another surface where you will see another this vector, so that is at xt. Okay, so that means if some trajectory is evolving like this, so in that case you will have different surfaces, and those surfaces will be okay. So that means the direction of the trajectory will be as per the different surfaces. That means here you will have some surface, and this direction will be like this. Here you will have some surface, its direction will be like this, etc. Okay, that means always trajectory will follow the surface phi x equal to, no, or this phi x equal to c. Sorry, phi x equal to c. Okay, so that means if we can write any function in terms of gradient of some scalar functions, then this x dot equal to fx, which is actually gradient of some scalar function, is called gradient system. And can you tell me about the Hamilton system, whether it is gradient system or not? Hamiltonian system. Can you tell me? Actually, if we have say Hamilton systems H having Q1, Q2 up to Qn, P1, P2 up to Pn. We will have 2n dimensions. Always we will have even dimension, and the degree of freedom will be only n. Degree of freedom is n. Okay. So we will have here Q1 dot equal to del H by del P1, and P1 dot equal to minus del H by del Q. Not P1, simply P, or it is Q. Okay. So we have this kind of, you can say, representation, which is actually equation of motions. Okay. So this can be written in terms of, say I'm writing x dot. So that x dot will be always j times of gradient of h, not simple gradient of h. That means where j is nothing but it is I, g, oh, sorry, 0, I minus I 0. So this I is n dimensional identity matrix, n into n identity matrix. Okay, and this is actually called asymptotic, you can say, system. So this shows that is volume will be always conserved. So for conserved systems, you will have this particular, this is not gradient system because it is not simply gradient of scalar functions. Here h will be constant total energy. So this is scalar function, but it is not direct gradient. We have to use j times of this gradient of h. After that we will have this x dot. Okay, so that means here in Hamiltonian systems, what will happen if we have this plane, this is plane, it is h equal to c. In that case, if I am starting trajectory from here, so it will not go in normal. This normal will be, this is gradient of h, but here j times of gradient of h will be in the plane. That means it will be in plane here. So this is nothing but it is j times of delta h. So always the solution will be there, trajectory will be on the plane generated by or surface generated by h equal to c. It will not go like gradient system. Now we will move to our system, that is applications of our dynamical systems for space systems. So we will have Lagrange functions which can be written in terms of kinetic and potential energy, that is kinetic energy minus potential energy, where potential energy will be given by, here d and r will be used to define the distances from the, say, sun and earth, or sometimes it may be moon, and suppose we have satellites, so we will have, say, d and r. Those are the values. Here we have satellites or some small infinitesimal body, and we want to see the motions of that particular points. So in 3D we cannot find these solutions of 3D solutions of 3 body problems. So we will have your 3 body problem, then restricted 3 body problems. Okay, so solutions in 3 body problem cannot be possible, but if we restrict one of the body, that is as a very small, which is compared, its mass will be approximately 0 in compared to other 2 primary bodies. In that case, it will be restricted 3 body problem, and our this system inertial frame will not be there. It will be rotating reference frame. Okay, so that means the restricted 3 body problem is defined in rotating reference frame, where the origin will be at the center of mass. So for sometimes we can also consider the center of mass as this sun, or sometimes it may be like this. This is center of mass, and we will have sun, and we will have earth, and we have some body m. In that case, the reference frame will be here. Okay, so it is also Newtonian frame, but it is rotating frames. But here the integral of motions will be Jacobi integral, which is given by We'll see here. Okay. These are the equation of motions. So this is 3D system, and in that 3D systems, we will have say x dot equal to fx. It is autonomous systems, and this fx here right hand side will be given by this partial derivative of u, where u is pseudo potential. It is not simple potential. It is pseudo potential. Okay. Here, these these two terms we are related to your potential energy, and this is due to the Coriolis force, and d and r are the distances we have already discussed, and there is only one constant which is actually Jacobi constant, and it is called Jacobi integral. Jacobi integral, and this is the only, you can say, constant, but other constant can also be seen here. Okay. So when kinetic energy is 0, in that case we can get the c equal to 2x by z equal to 0. Okay. Or it's not 0. C equal to 2 times of u x by z. So that means we will get one you can say potential function, which is function of 3 dimensions, like 3 variables x, y, and z. If we can use in 2D, in that case you will have c equal to 2 times of u x, y. Okay. So for particular value of c, we will have different curves. Those curves will be our zero velocity curve. That means we are considered here z equal to 0, as well as x dot equal to 0, y dot equal to 0, and z equal to z dot equal to 0. That means these are the surfaces or curves which are obtained by taking velocity equal to 0. That's why those are called zero velocity surfaces. So we have obtained zero velocity surfaces here. Now you can see this is the sun, and we have earth here. Now we have forbidden regions here. In this particular regions, the satellite can move, but in other regions satellite cannot move. So these are the regions where it can move. So those regions will be applied for trajectory transfers. That means here, if we will have some equilibrium point and we have stable and unstable manifolds, then those will be used to transfer the trajectory from one place to another place using this zero velocity curve. That means at a particular value of the Jacobi constant c, so at particular value, we will have a specific kind of this contour plots of zero velocity, and accordingly we will see these forbidden regions will be different. Sometimes for a particular value of c, this forbidden region may be very large, sometimes they may be very small. Okay. Now we will have, next thing is Lagrange equivalent points. So x dot equal to fx, we will have our autonomous systems x equal to 0, fx equal to 0 will give equivalent point. That means here in our that equation, these equations, right hand side we will make 0, and we will find equivalent points. Those are actually called Lagrangian equivalent point, because those are found by the Lagranges. That's why they are called Lagrange's equivalent point, where acceleration and velocities component will be 0. Okay. So solving these equations, we will get these equivalent points, where L1 is here polar equivalent points. Suppose we will have here sun, we will have here earth. So we will have here it is L1 and this is L2, and we will have L3 here. So these are actually collinear points. These three are collinear points. Collinear points. They are actually unstable points in linear sense. But we will have some more points. Two more points. Those are stable in linear sense. Those are called L4 and L5 points. Okay. We here actually we want to transfer the trajectory from one, you can say, Earth parking orbit to the hollow orbit of Lagrangian points, that is linear that is collinear Lagrange points. That's why we have obtained only collinear equivalent points of different cases like Sun Earth system, Sun Mars system, and Sun Jupiter systems. So those are written in kilometers. Okay, you can see here. This is our Sun. Say it is Earth. This one is Earth, and we will have this may be considered as M1, and next one will be may be considered as M2, and that L4 or means this may be considered infinitesimal body position. So that means equilibrium point may be considered as the position of our body, so that we can check its stability. Okay. Now, if we enlarge that particular plot, we have seen for different values of C. You can see these are the different values like C equal to 3, 3.5, 0.05, 3.01, up to say 3.003. So for that particular region, we will have here equilibrium point. Sorry. This is L1 and this is L2, and here it is Earth. Okay. So around L1 and L2, we will find orbits. Those orbits will be periodic orbit, and those periodic orbits are very sensitive. You cannot directly find those orbits. They require, you can say, a specific initial guess to find the periodic orbit. And they are symmetric 3D orbits. So now, if they are 2D, then they are called Lyapunov orbits. But here, if we are using 3D, then they are called hollow orbits. Okay, and these are the forbidden regions. That means this region is forbidden, where trajectory cannot move. This is the forbidden region. Forbidden region. Okay, here any you can say satellite cannot move this particular region. Now we can write our system in terms of x dot equal to fx fall, because that was you can say second order differential equations. But here we can change the right hand side values in terms of different other you can say component, and those can be written in terms of x dot equal to fx. So this is our suppositions, and differential equations will be like this. This is our x dot equal to fx, and here actually this is nothing but it is fx. This one is not fx. This is x. This is my x. Okay, that means we will have 6-dimensional space. If we are considering 3 dimensions, so now becomes 6-dimensional spaces. Okay. So we will have components x1, x2, x3, x2, x6, and we will have 6 apps. Okay. So now to find the characteristic of equilibrium points near the L1, L2, or L4, L5. So we can consider the Jacobian, and the Jacobian will be given by the derivatives of partial derivatives of right hand side functions f's, and those can be written in this form: phi x0t equal to different order derivatives of like x. So this is actually called, this is Jacobian, or sometimes it is also called state transition matrix, because we use this particular you can say like we are writing x0 equal to d of f x0 and x0. So this one is actually your phi x0 t0 or t. So this is actually your Jacobian or state transition matrix, because you will apply this dfx0 over and over on x0, so that you will get the trajectory at different times. Okay. Now here it is a 6 into 6 matrix. Okay. So at initial value it will be 6 into 6 identity matrix. Okay. So this can be written in terms of, if you want to find variational equations, we are substituting those values in our differential equations. Then we will have a differential equations in matrix form. This is actually differential equations in matrix form. What is the reason why we want to find this matrix? Because if we have say something near this x0, means x0 means here our initial point, and we want to see the nature of the nearby trajectories. That means we have to make the flow of this particular trajectories. Okay. So to see the flow at different time, so we can use matrix differential equations, and we can get the nature of this nearby trajectory with respect to the original trajectory. Okay. Okay, so state transition matrix is propagated using this variational equations. This is sometimes also called variational equations. Ax is actually, it depends on time. It is not constant matrix. It depends on time. Okay, the partial derivatives are written here. Now to find the hollow orbit or any periodic orbit, what we do, we use sorting methods. Suppose this is periodic orbit, and it is say symmetric about this axis. So we will use only say 0 is here, and at t times this trajectory will go here and it will come here at the its initial position. That means here this timing will be t by 2. Okay, so for half period, that means from 0 to t by 2, we will find the solution and then it will be projected. But always this case will not be same. What happens if we are finding this periodic orbit, so it should come at the initial position, but sometimes it may not come at the initial positions, it may come here. Okay, so this is the difference. This is our final destinations df, and this is my d0. So I'm starting from here and I want to reach at, you can say x0, it is good, x0, and this is say xf. I want to reach at xf, so xf will be my this one, but I am not reaching fx at first iteration or first you can say suppositions of the initial guess. I am coming here. Okay, so what will happen? That means this is the difference. We have to correct this difference. So we use sorting method that is called differential correction methods. So that means we will correct this initial guess. This is initial guess. Initial guess. So initial guess we will choose, and we will correct this initial guess by looking the final difference. Say we will have some difference. This difference will come here. So we will reduce this difference by using differential corrections. Differential correction method is actually Newton's method. So instead of using this full, you can say full t means full time t, that is capital T, we use only half t. That means it may pass this red dot. It is correct one, but instead of going this red one, it is going somewhere else. It is going here. So this is the difference. Okay, so we have to correct this difference so that it can be projected, because it is symmetric with respect to x-axis. So this particular orbit can be generated accordingly. Okay, so for that purpose, it is symmetric. That's why we can suppose that y is 0 and here x dot 0, z dot 0, and y dot is like this. Because y dot is positive, we are considering positive in this way. It will come like this, and whenever it is crossing, y dot should be negative. So those things we will consider, and we will also, this time t by 2 will not be same. Sometimes it may have t1 by 2 plus some delta t by 2. Okay, so this delta t can also be changed as per the value of initial condition. We are supposing initially here, then it may come here, then it may come here, then it may come here. So similarly, this delta t will also be modified accordingly, so that for at actual initial you can say position, this orbit will be our full periodic orbit instead of some other orbit. Okay, so all these things will be you can say corrected. So these corrections we will make. So actually we will use differential correction method. That means it is Newton's method. In Newton's method, we have to solve here like x delta x is say d of say delta x0. So that means d delta inverse x0 say. So what we do to find x0, we will use delta. This is delta x0. This is delta x. So this is a delta x0. Okay. This is d inverse, is derivative. So what we do, instead of using inverse of this matrix, we use delta x0 equal to d of delta x. Okay, so this system of differential equations is solved. using a particular method, any method we will apply, and then this will be corrected. Initial guess will be corrected accordingly for half period of time. So we have taken the initial values. Okay, so this is actually our matrix, which will be used to find the solution. That means we will have 42 system of equations. We will have 42 system of equations we have to solve simultaneously. Okay, so by taking some specific values, say if I consider some of the initial values fixed, in that case some of the things will be 0. That means if I am considering x0 equal to fixed, that means delta x0 will be 0. So some of the equations may be reduced. That means you cannot use here, means there is no need to use 42 equations. You can use a small number of equations by taking some of the component fixed. Say I am taking x0 fixed. So in that case, delta x0 will be 0. Okay. So we can solve only this differential or this system of equations. This is here inverse. So we can take left hand side and we will solve using Newton's method. Okay. So that will be done. So after solving after correcting the initial guesses, so initial state that was this, and after half period it was this, and this is correct one. Whenever I take full round, it will coincide with the initial case. So these are the correct one we have obtained using this differential correction method for all the three cases here. Like you can say this is for L1, and for one you can say value that is for L2. Okay. Now next thing is stability of the hollow orbits. Now using these initial guesses, we can find hollow orbit about L1. So we will have obtained this hollow orbit. Okay. Its shape will be like this. Okay. So this is periodic, but it is centered. So it is very structurally very unstable. So what we can do, we can use some mechanism so that the stability of this orbit can be found. So what we do, we can use say PSS, Poincare surface sections, and at different, you can say, values, say initial value, I am considering this initial value, and I will see at the later stage where it is coming, maybe here or somewhere here. Now it becomes circle, but it should not be circle like this. So it may be here. Okay, so that means it is our discrete map, and that discrete map is if it converts to its initial positions for later time. In that case, this periodic orbit will be stable. So what we do to find the stability of the periodic orbits, we will use Jacobian of linearized system of this map, which is generated on Poincare surface sections. Okay, and their equilibrium points we will see. Oh, sorry. Their eigenvalues we will use to see the stability of this periodic orbit. Okay. So we will discuss the stability of those points. So that means we have taken the nearby value, that is delta x, delta z. That means variational equations we will use, and accordingly we will see at the last what are the values of their lambdas. Okay, like here. So it is known that the Monroe matrix. Actually, if we have, say, this is the flow. So STM is nothing but it is simply d of f at x0. This will be STM and will be used to find the flow at different time. But if we are considering periodic orbit, so if I am starting from here, it will come here. So at 0 and t time. So at t time, this STM at t means one period is called monodromy matrix. Monodromy matrix. Okay. So if suppose I am here and this is Poincare surface sections, I want to see stability of this periodic orbit. That means I have to only check the point crossed by this perturbed orbit on that particular sections PSS. Okay, so it means at one period I have to only consider the changes made in this particular map. Okay, pointer map. Okay. So that means here at t, means after t, after one period, this state transition matrix will be my monodromy matrix. So this it is actually Jacobi matrix, and this is actually generated nearby for nearby trajectory. Suppose this is a nearby trajectory, nearby point. So for that nearby point, if vector is there, this vector will be evaluated using monodromy matrix, so that at the later time you will see this same trajectory. But evolutionary trajectory is not required. Means the solution of the whole you can say equations using new initial guess is not required, because you have already considered one point here. This is the your actual point on the periodic orbit, and there is nearby point. This is the nearby point. Here you want to see if this periodic orbit is you can say disturbed by some you can say distance. Then at the later time whether it will come on this initial point or initial orbit or not. So that can be done by again designing the another orbit, but it is not good. Only thing we use monodromy matrix at after time t, and we will see the eigenvalues of those monodromy matrix, because in that case the evolution of the this deviation is same as generating the new trajectory at distance this deviation. So this is delta x. So if I am evaluating this delta x using monodromy matrix, then it is good. Otherwise, what we have to do, we have to use another trajectory, and we have to find new orbits. So here for the complex eigenvalues accommodative conjugate, hence the stability absolute value of eigenvalues must be unity. For stability purpose, it should be 1 or less than 1. Okay. That means if it will be in orbit, so it should be 1. Okay. Or it should be less than 1, so that we can see it is hollow orbit is stable. So we will use here monodromy matrix to check the stability. Now here in continuation methods, we will have this is hollow orbit. It is periodic orbit, or you can say center in our this system. Okay, so in continuation methods, if we use different values of parameters, so you can see different hollow orbits can be generated using continuation methods. There will be a lot of hollow orbits we can generate. Initial guess for this first one, you have to find the initial guess. Initial guess using differential correction method, DC method. But for others, there is no need to find again initial guess. Only we will use continuation method, and for perturbations, and we will get different hollow orbits. These are the projections, different projections of orbits. Okay, and different cases like Sun Earth, then Sun Jupiter. This is for Sun Jupiter cases. For other cases. Now next is invariant manifolds. Okay.
Sir,
What happens if we have, say, you will have this is
you
the
will
equilibrium
have 5 more
point.
minutes, sir.
Just it will take a little time. No.
Yeah.
So suppose this is the equilibrium point, and we will have say, okay. So this is say unstable direction, and this is say stable direction. Okay. Now we will find eigenvalues of monodromy matrix at different, you can say, suppose eigenvalues of the Jacobi matrix. Okay, Jacobi matrix is there, and we will find eigenvalues. Say we will have say lambda 1, lambda 2 up to lambda 4, just not for 2D case, just we understand, so that we can define it is for n dimensional case. Suppose it is only 2D case, so there is one direction. Now this is the same vector, means vector corresponding to lambda 1 positive, and this is say lambda 2 negative. So no, sorry, it is positive and it is both are unstable. Just not. I should write in this way. I think this is good. Okay. So for this is stable direction, and this is unstable direction. This is unstable. Okay. So if vector corresponding to this eigenvalue say lambda 1, which is less than 0, So we will have v lambda 1. So v lambda 1 will span this particular direction, this direction. This is stable direction. So this will be span by eigen value with real part negative. You consider real part negative, and this will be spanned by the eigenvector for real part greater than 0. Okay, and this particular dimension, or you can say curve, which is spanned by this particular space, which is spanned by this eigenvectors for which real part is greater than 0, is called unstable manifold. Unstable manifold. So that is in linear case. Actually, we are using this is for linear case. This is for linear approximation. Okay. Similarly, this particular space, which is spanned by the eigenvalues whose real part is negative, this is called stable manifold. Stable manifold. Okay. Now we may have some directions where real part is 0. In that case, it will be center manifold. Okay, center manifold will be, that is for which real part of lambda equal to 0. Okay, so that means we will have, these are the dimensions of a spaces in linear sense, but the straight line will not be this kind of a straight line in nonlinear sense. In nonlinear sense, what will happen? You may see this particular this unstable manifold may not be like this. So if we use nonlinear case, so it may be like this. Okay, similarly it may be like this because it is in nonlinear case. So this may be considered as WU. So this is actual manifold in this unstable manifold in non-linear system. Okay, similarly here this may not be same, it may be like this, this may be like this. Okay, so this is your W say S. So this is stable manifold. Stable. So what is the property of stable manifold or unstable manifold is that if something is on that particular or inside that particular space, then it will always be in that particular space. Suppose some point is here, so it will be on this particular you can say manifold only. It will not go anywhere. For when time is increasing, for stable manifold, it will converge to the equilibrium point. This is x bar. Okay, but for unstable manifold, if some point is there, it will be always an unstable manifold. It will remain there. It may go. It may, if time increases, it may go to say infinity. Say, but it will be always on that particular manifold. So that means in manifold here, that's why it is called invariant, because if something is there, it will always be there on that particular manifold. It may move anywhere as per the kind of manifold we are using. Okay, so around L1 and L2 hollow orbits, we will find manifolds. To find manifold, what we do here, we will use our say hollow orbit, and we will take some perturbations, perturbations we will take, and like this. So suppose we start evolving the trajectories about nearby in the orbits. In that case, suppose it may be say unstable manifold you will generate. Similarly, some things you may see like this, stable manifold. So in forward and backward time, that is say in forward time, this is in backward time. Same thing may be considered as a stable or unstable in a periodic orbit. If we are using say negative time and we are evolving, then it may be stable. Here it may be unstable. Computation of manifold, we will take initial perturbations with the orbit, and we will evolve with our you can say state transition matrix. So we will get manifolds. Now trajectory transfer. What we do to transfer trajectory? Suppose this is the parking orbit of the Earth, and we are starting from here. And suppose we have hollow orbit here. So suppose I want to transfer from here to here. So we will place this orbit, this particular you can say satellite along the manifold of this particular hollow orbit. Say it is hollow orbit, and see this is stable manifold of the hollow orbit. So we can place, and we will use simple perturbations. Say it is V at parking orbit and V at say hollow orbit. So that means here Vp minus V hollow orbit minus Vp. So that delta V means delta V, this particular velocity change is required here, and it will be placed on the hollow orbit. Oh no, stable manifold of hollow orbit. This is L1, and it will go to that particular orbit. And here it will be attracted by this stable, you can say, periodic orbit. So here you will see, like here we have generated some of the stable and unstable manifolds. So you can see this is L1, and here these are actually we have divided into interior and exterior kind of manifold, because for positive means forward evolution and backward evolutions. So one kind of orbit may be considered as the other kind, like stable may be unstable, unstable may be stable, because here say it's the exterior. So this red and pink, those will be here. One will be interior, another is exterior, but they are stable. If I am calling this pink one, so it may be say unstable in other case. If I am using say this is forward direction, this is forward direction of t, and this is negative direction of t. In that case, this may be say considered as the stable, then other will be unstable. Okay, but I am considering interior and exterior. That's why both are calling stable manifolds here. So you can see here, if something is placed here with the stable manifold, so it will go like this, and it can come here like this. Similarly, if you want to transfer trajectory from here from hollow orbit, then what will happen? We use unstable manifold, and with the direction of the unstable manifold, it will go to the Earth parking orbit. That means without any extra fuel, the trajectory can be transferred. Generally, it happens if we are considering the amplitude of this particular direction, amplitude of this particular hollow orbit as 11,110,00 kilometers, means 1,10,000 kilometers. Similarly, this is other case. Okay, now so this is for L2, and previous one that was for L1. So we will have similar kind of orbits for L1 as well as L2. Our Aditya mission is proposed around this L1. Aditya mission, Aditya L1, say Aditya L1 mission is proposed to launch around L1. So this is L1 here, and we have two kinds of orbits, like stable and unstable manifolds around L1 and L2. Two orbits, that is hollow orbits around L1 and hollow orbits around L2. Okay, so these are for different cases. You can see now how to transfer the trajectory. You will see here. This is actually combinations of both the kinds of orbits. You can see you will have L1. This is L1, and this is L2, and this is Earth. So if we place the satellite in a particular stable or unstable orbit, then it can be transferred easily due to the properties of the dynamical system, because our dynamical system is very sensitive dependent dynamical systems. Small you can say fuel can depart it using unstable manifold or stable manifold. So that is you can say one kind of important use of dynamical system theory for efficient or fuel efficient trajectory or time efficient trajectory design, which was used by NASA using Genesis method, or they have launched Genesis mission and ISE missions. Okay, you can see this is trajectory transfers. We have here we have used, and they have we total transfer trajectory time was 207 days, and we consider 300 points, and we have optimized which point will be optimum for transferring trajectory from Halo orbit to the Earth. Similarly, we have also done here that have taken to 1 days to transfer. This is actually our Halo orbit. Suppose I'm here in Earth parking orbit, so it will go like this, and it can be transferred, and it can move around L2, but it will not be always L2. So we require continuous maneuver so that it will be always around L2, because say our India is planning to launch Aditya mission around L1. So that L1 is not because it is periodic orbit, it is center, so that is very unstable kind of thing. So small perturbation maybe due to fractions and other, or some other reason, so it always the altitude of this will be decreased, and it will then it may not be on the nominal orbit. It may go anywhere. So continue maneuver is required to control this. So that can be done by using another fluctuate theory. Fluctuate theory is used to you can say control the object around the periodic orbit. Again we use the eigenvalues and eigenvectors. So this is actually not time optimum trajectory transfer, but it is very much fuel efficient trajectory transfer. It is taking more time, but it is using the Halo orbits, manifolds of L1 as well as L2. This is L1, here we have L2. So it is using the Halo means manifolds of both the equilibrium points like L1 and L2. So it is taking very small fuel for transfer, and Genesis mission used this one. Genesis this kind of transfer you can see on internet. You can see Genesis mission have used this property of dynamical system for transfer of the trajectory. Thank you, sir.
Thank you, sir. Thank you. So
So,
it's time for questions. Or some clarifications.
yes, anyone want to ask anything, you can ask related to the topic.
Sir, is the Lyapunov exponent and the Lyapunov stability same?
No, Lyapunov actually, what happens, both are not same. Actually, in Lyapunov exponent, Lyapunov exponent, mainly it only measures the um, average divergence of the nearby trajectory at the later time. Suppose we have, say, this is the actual trajectory, and we are starting from say x at t0, and here we have x at t, and suppose we are taking some nearby point here, then how this trajectory is behaved. Suppose at the later time it may reach here. So this is the major difference. Okay. So what we do, we use the cell, say we are using say lambda t and say x0 here, but instead of using this, what we use lambda 1 by say t. Average the rate of you can say divergence or convergence is called Lyapunov exponent, where ln x t and x0. Okay, so this thing can be, you can say, break into different part, because if you are using numerical computations, so directly you cannot handle large and small things, because suppose it's in a one direction. Suppose we are using in one direction, so this may be considered over one or two directions. This may be considered as a volume. So here that may be say circular, you can say circular area, circular, you can say, or orbit, or sorry, just a minute. Oh. So you can consider nearby point maybe your circle, say having say x and y axis, but at the later time you may see this kind of things may appear. Okay. So here this is the larger direction, and this is smaller direction. So suppose this is corresponding to lambda 1 and this is corresponding to lambda 2. So this is stretching in one directions, okay, and compressing in other directions. So this volume is now expanding, but it is expanding in terms of you can say stretching as well as rotating or translating also there. So this particular directions at the later stage will be very much you can say problematic while computing. So what we do, we use normalizes, so that this can be again taking at the initial value here, again circle will be there, and this circle will be again evolve, and at the later time again we will normalize, denormalize, and we will do it. So actually in a particular direction, suppose in a one direction, so the maximum expanding direction, maximum expanding direction. Suppose this is you can say having a small value, it is not it is, or you can say it is finite. In that case you will have stable conditions. Otherwise what will happen, if it is steering and it is going to very large value, in that case you will have a sensitive dependency of the system. So it is different from our stability. It measures only the sensitive dependency of the initial conditions.
Oh, okay, sir. Thank you.
So, any other question or clarification?
Sir, I have one question.
Mhm.
How to use this Floquet theory to control this orbit? Because I have listened that Floquet theory is applicable to a non-autonomous system.
Actually, that can be applicable for non-order system. But what we are using here? Just a minute. I have written somewhere. Na? Say here. What we do here? Suppose this is my periodic orbit, and we have taken say Poincare surface sections here, that is PSS. Okay, and this trajectory, it may be means in it may cross here, and here we will say Poincare map. We will have Poincare map. So xn plus 1 equal to fxn. This kind of map we will have. For this map, we apply Floquet theory. That means here we want to see only whether these points will converge to this initial orbit or not. So that means here, if you want to control the nearby trajectory for later time, that means if it is going somewhere, it means some fuel is required to maintain this distance. Okay, and whether it is going far and away, so that can be seen by taking the eigenvalues of the monodromy matrix, and those eigenvalues are actually called here Floquet spectra. Floquet spectra, है ना? Floquet spectra. So those Floquet spectra or multipliers, say you can say multiplier, है ना? Multiplier are used to check the stability of the periodic orbit. That means if modulus of lambda is less than 1, that means it is you can say having or it will not diverge. If it is means modulus is maximum, the particular lambda which is maximum, means all the lambda should have less than or equal to 1, you can say absolute value. Is it okay?
Yeah, can you?
Is there any confusion?
Yeah. Any other question? I think we are not getting any other question, sir. So,
Thank you. Thank you for.
since I'm not getting any questions, let us conclude the session. So I wish to thank. Let me conclude this session by thanking Dr. Badam Singh Kushal for giving a very interesting talk. I mean, he applied the nonlinear ideas to astronomical problem. It's a very interesting talk, sir. Thank you for accepting our talk and giving a lecture here. Thank you, sir.
Thank you for giving me this opportunity for giving the talks. Thank you, sir.
I will write to you the other formalities.
Okay. Okay then.
Okay. So you can.
Yes. Should I close my?
Yeah, you can leave, sir.